In this video, we will build and train a sequence-to-sequence model. Since we have already seen the preliminary steps that we do in TensorFlow, let's go directly to the code. We will do two models, one faster on a reduced set of data to see all the pipeline in a faster way, and the other on the whole set of data and different parameters that we will show to see what is the level that we can reach with more computation. So let's start loading the packages and read the data. As we said, our languages are English and Italian. We start from English and we translate it in Italian. You are safe in English, è al sicuro in Italian. Now, let's do the typical text processing steps, but we don't remove stop word. If you remember, in the language classifier, we said that stop words do define the language, so they are useful. This is a very important trick. Notice that we add start and end at the beginning and the end of each sentence. This is to have some kind of delimiters that will tell our decoder to start and finish, because we don't have general signals of start and finish in natural language. You don't say, I am okay, end of the sentence. So basically, end reflects the point in which our output sentence is more likely to end. Notice that we still use 5,000 words because they don't affect computation. The length of the sentence does affect, so we use 15 as a length. We will increase this in the next model. Again, we tokenize, fit on text, text to sequence, and then path sequences. Now, notice that we have two tokenizers, one for English and one for Italian. Okay, let's start with the architecture. We have the Italian text, that is the input of the decoder. Then we have the decoder target that uses vectorized Italian. English is the input of the encoder, and the document length is the length of the data. Here we have 90,000 because we left 10% out to validate the model, in real time, obviously. So, do you remember vocabulary size? So it is the same, okay? And this is the same for encoder and decoder. So, let's assign this value to our variable and remember to add 1 for the padding character. We set the length of the embedding space, the dimension of the embedding space, and then let's start with the architecture. We have the encoder inputs, okay, that is the size of the vocabulary of the encoder. Then we do a batch normalization step. The distribution of the inputs of a specific layer doesn't change over time. We don't need the output, we need the state, okay? So this is the output of our model, of our encoder model. These are the decoder inputs that are initialized here, like here, and that have as an input the size of the decoder. Again, batch normalization, and this is the first decoder neural net. We end up with a dense layer, and then we have the final model that we compile. We have the encoder inputs and decoder inputs that are the model, and the decoder outputs that are the outputs, of course. So let's run the architecture. Again, we summarize the architecture, and then we train. Let me also change another parameter in order to be faster. We don't want 6 epochs, we want 1. You see, it's taking 5 minutes. Let him work, and in the meantime, I will show you how complex it is to decode the model. So we have to regenerate all the outputs. Remember, in the first video, we do the predictive part in which we do the input, we give the input, and then we have one output. But this time, each input is the output of a given model. Okay, so this is much more complex. Again, we use the sparse categorical cross-entropy, the softmax. Nothing new on the function side. The evaluation functions are always the same along this course, these videos. We could also, for example, choose even a smaller set of data. Maybe it would be faster. Okay, training is done. We have another important tip is that we can save the model, as you can see here, and reuse it. Okay, so let's start evaluating this very simple model, probably weak model. So let's start with a simple sentence. This, that I like food. We have to tokenize it based on the tokenizer, the first tokenizer, the one in English. Okay, we do the sequence that we know already. So we encode it. Now we need the latent dimension and we get the layer. So we get to the decoder word I'm adding that gives as output a latent dimension. Okay, and then we get the other layers. So our latent dimension now becomes the input of the inference state input. Okay, we need the inference state because it will be again the input of another layer that in the end will be the input of the decoder layer. But let's do the step one by one. We are now decoding, okay, and now we need the state value. Every sentence, the initial value corresponds to the position of the start word. Do you remember the example at the beginning in which in natural language you don't say I am starting a sentence and then you mention the sentence, but rather you say the sentence that starts and ends. So as we said before, we need a starting and an ending point, okay? And it's always like this because we have decided it, we have defined it at the beginning. Let me show you again the code in order to be more clear. There we go, start and end, okay? So when this word occurs, then it's the initial state. Okay, so this is state, and the state value is an array of 1. Now we initialize the decoded sentence, and we use a stop condition. Which are our stop condition? One is that the length, okay, exceeds the maximum length that we defined at the beginning, okay? And the other, which one is the other? Well, the other is exactly that at some point, the word that is more likely to occur is exactly this one, end. Okay, so while decoding, in a certain point, the models say, okay, now it's more likely that I found this word. And if I find this word, the end of the sentence is here. Let me show you again. The predicted word is end, or the length exceeds the predefined length. Let's see what we get. È fatto suo, 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 suo. Wow, very strange sentence, but the model is weak, as we said. But we see that not only that the meaning is not correct, but also the length is totally wrong. We have 3 words, and then here we have a very long sentence with a word that is repeated so many times. Okay, so now it's time to try to work with another model, a much powerful one. If, for example, we go to Google Translate here, and we type I like food, mi piace il cibo, I like food. Okay, so totally wrong translation. Okay, let's go to the other model. Okay, let's start with the more complex model. We load the packages, and then we read the data. Notice that this time we want the whole data set, and we don't select the rows. Okay, so we print the data. We see that we have much more data, 289,000 and to train and 32,000 to validate. And then we make the steps that we made previously. Again, remember, this is an important part because we say that with start, we know that the sentence is beginning, and we say that with end, the sentence is ending, okay? So now notice that we keep the 5,000 maximum words, general words, that can occur this time in sentences that can be length 35 words, okay? In the previous model, it was 15, so much more computational power, expensive. We see that it takes more time to tokenize and to do the typical steps that we do in English and Italian. Remember, this is the different part compared to our language classifier. We define already the model architecture. We see that the dimension has changed. We keep the dimension of the embedding to 40, it's enough, and then we define the model. Now let's train it. Notice that we have set the number of epochs this time to 6. So much more data. The sentences are much more big, much more words, and then we do much more epochs, 6 times. You see, it takes 1 hour per epoch. Okay, so training has finished. You can notice that this time we don't have 5 minutes per one epoch. Okay, we have rather 4,000 seconds, which almost are 66 minutes. So let's say 6 hours to train our model. We expect better results this time, hopefully. Let's start with the same sentence as before. Do you remember that I like food? In Google, translate was mi piace il cibo, like this. Okay, so let's see what do we get now. Very quickly move through the different steps, and then we see that again, this is the state, the starting state that belongs to the word start. Remember, this is a key point of all this video. Okay, which was the vocabulary, and then let's see the output. Mi piace. Let's copy, and we will show you that it's the same that we wrote here. What is the difference? The difference is that here we have mi piace il cibo, okay? And here we only have mi piace. But it's not that bad, because he understands that I'm talking that I like something. I like, okay? He doesn't understand that I like exactly this in Italian. But still, if you remember the previous translation that was completely wrong, we are getting closer to the real meaning of the sentence in Italian. Let's start with another sentence. Is waiting for you. Tom ti sta aspettando. This is a more complex sentence. Wow, Tom sta aspettando. Let's copy again here. Again, he understands the model that Tom is waiting, but not for who is waiting, okay? But let's see what we would get in Google Translate. Let's copy everything here, and then we drop the Italian. Tom is waiting for you, okay? Tom ti sta aspettando. So Google Translate works quite better. Understands, compared to our model, understands who is waiting for Tom. But again, we are talking of Google Translate. This is another story. We have done a model in 6-hour computation with my computer and with a corpus that is 18 megas. Okay, so our result, I think, is satisfactory. Let's try another sentence. The weather is bad, which is... Notice that for each sentence, we have to repeat all the steps. You see how complex it is to build a machine translator and to put it in production. Imagine that every time that you type a sentence in Google Translate, basically you have something similar to grazie è piuttosto. Okay, this is more complex and we have a bad result. With this we finish. In this video, we have seen how to build a machine translation system. Now it's time to move to another section in which we will build a topic classifier for fake news.